What exactly is the difference between adding a negative number and subtracting a positive number? You must have learned a plus b equals ab, which is a theorem. But I wonder if you've ever felt a slight confusion. Are they really no different? Formal systems in algebra pursue simplicity and universality, defining subtraction as the inverse operation of adding a negative number. However, the human cognitive system is not organized axiomatically. Subtraction originates from the psychological model of taking away. Adding a number smaller than 0 cannot be mapped to this intuition. Algebra tells us they are the same thing, but the brain says they are not. Is subtraction a special case of addition or an independent and equal operation? The correct answer depends on who you ask, and everyone's answer is correct. Algebraists say subtraction is adding a negative number, mathematicians say subtraction is much older than negative numbers, and cognitive scientists say children's brains treat addition and subtraction as two separate procedures. All of them are stating facts, merely observing different facets of the same object. This is like imagining algebraic structures as the blueprints of a building. Addition is a load-bearing wall. Its position and specifications are clearly drawn on the blueprint. Subtraction is an interior door. It certainly exists and is useful, but it's not specially marked on the blueprint, because a door is equivalent to an opening in a wall plus a door frame. It's implicit common sense. You can feel the presence of doors when you live in the house, but an architect designing the load-bearing structure wouldn't treat a door as an independent mechanical element. If the story of algebra is subtraction is dependent on addition, then the story of history is entirely the opposite. Subtraction existed independently for millennia, while negative numbers arrived much later. Ancient Egyptians, around 2000 BC, used legs walking left to record subtraction. Subtraction survived for at least 4,000 years without relying on negative numbers. Negative numbers were a concept invented/discovered later, used to explain why subtraction could produce results smaller than 0. From this perspective, subtraction is primary in history, and negative numbers are secondary. So, are algebraic operations completely different from primitive natural number calculations? The answer is subtle. The results of the operations are consistent, but the objects and meanings of the operations have changed. So, how did algebra itself come into being? Why did it take humanity so long to move from concrete arithmetic to abstract algebra? Because algebra is not a natural extension of arithmetic, but a new language invented by humans to solve problems that arithmetic could not. Ancient Greeks encountered a fundamental dilemma. They discovered that square root 2 was not a ratio of integers, yet their mathematical philosophy did not recognize irrational numbers as legitimate. They circumvented this contradiction by using geometry, solving problems by drawing geometric figures, making it an appendage of geometry. Later, Al-Khwarizmi wrote algebra in the House of Wisdom in Baghdad. The second driving force behind algebra, practical needs. Al-Khwarizmi explicitly stated in the preface that he wrote this book to solve problems frequently encountered in inheritance, estate distribution, commerce, and land surveying. A universal algebraic method was far more efficient than repeatedly solving individual arithmetic problems of the same type. He categorized all first and second-degree equations into 6 standard forms, provided general solution steps for each form, and proved their correctness using Euclidean geometry. However, the limitations were also clear. Al-Khwarizmi's algebra was entirely verbal, without symbols, and he still did not accept negative solutions. The real leap came from the crisis of cubic equations. Cardano published solutions for cubic equations in Ars Magna, but describing the solution steps verbally was so complex as to be almost unreadable. A single equation required several pages of textual description. Verbal algebra hit a ceiling. After the spread of printing, Veit began using letters and symbols instead of verbal descriptions. Veit's approach, A plus D equals B. Not only unknowns but also known numbers and coefficients were represented by letters. Historian Jacob Klein said, Veit's letters were not abbreviations. Instead, they were symbols in the true sense. representing types of quantitative relationships rather than shorthand for specific numbers. Finally, Descartes, in 1637, began using the algebraic equations we now know to express geometric curves. A circle no longer needed to be drawn. It could be described by x superscript 2 plus y superscript 2 equals r superscript 2. At this point, algebra completely replaced geometry, becoming the fundamental language of mathematics. So, what exactly is the difference between adding a negative number and subtracting a positive number? The answer is, in algebraic structures, there is no difference, but in the history of human cognition, they have never been the same thing. Formal systems continuously compress concepts, unifying multiple operations into a more concise structure. However, the human brain is not built axiomatically. Children do not naturally understand subtraction as adding a negative number. Ancient civilizations also did not invent negative numbers before inventing subtraction. On the contrary, humans first had the experience of taking away, and only millennia later created negative numbers, eventually using negative numbers to reinterpret subtraction. Thus, a peculiar phenomenon emerged. Historically, subtraction existed before negative numbers. Cognitively, subtraction exists independently of addition, but in modern algebra, subtraction has been dissolved into a special case of addition. Mathematics does not negate intuition. It merely stands at a higher structural level, compressing multiple originally different actions into a single type of relationship. And what algebra truly changed was never calculation speed. What it changed was, the legitimacy of mathematical objects no longer depends on whether they can be intuitively experienced, but only on whether they can be embedded in a self-consistent structure.